Okay, exploring the solar system, part 6. And don't worry about the fact that you haven't had part 5. These are all independent parts of the exploring the solar system theme, as it were. This one, although it's the last one, you could argue this should have come first, but no, I wrote this last of the 6. This is, where did our solar system come from in the first place? How did our solar system form? What clues do we have? What do simulations tell us? Because it happened a long time ago, so we can't study it as such, but we can simulate what we think happened. And what questions do we have? But of course, this also ties into the fact that if we look at what's going on in other solar systems, we might be looking at other solar systems in the early stage of their formation. And therefore, in a sense, we might be looking at what happened in our solar system maybe billions of years ago. So this wonderful little brass orrery, I didn't bring it with me because I didn't really think I had enough space on the front table here. But if you're building a brass orrery and looking at how planets move around the sun, well, you build it from the inside out. You start with the sun and then you add Mercury, Venus, Earth, Mars, etc., and you build out. But that's not how the solar system was born. It wasn't born from the inside out, as it were. It was, in a sense, a lot more complex than that. This is a star-forming region. It's called the Rho-Ophiuchi Molecular Cloud Complex, a bit of a mouthful, but basically Rho-Ophiuchi is a star and it's surrounded by this cloud system. It's about 400 light years away, which is relatively close on the scale of the galaxy. The galaxy, remember, is 100,000 light years in diameter. So 400 light years is one of our neighbors. And this is the closest region of a hydrogen cloud in which stars are being born. Hundreds of new stars are being born throughout, not just in the bright patches, but throughout most of this particular field of view here. And there's enough mass in this cloud of hydrogen to make thousands of stars and thousands of solar systems. And we believe that our sun and our planet were born from a similar cloud of hydrogen collapsing under gravity and eventually forming the star, and what was left over after the star was made is effectively the planetary system. So to give us a sense of scale, otherwise a scale of time, otherwise it gets very difficult to sort of get your head around what was going on, I've got this logarithmic scale here of time from when a large cloud of hydrogen collapsed to form a star, million years, 10 million, 100 million, and then effectively present day is squeezed right to the right-hand end of this particular graph. Don't worry about T Tauri. T Tauri is just the name given by astronomers to a particular type of star, which indicates that when a cloud of hydrogen is collapsing, it gets hot. And T Tauri is just the name for this prototype star, as it were. As the cloud collapses, it starts to get warm, simply because it is trading off gravitational energy to heat energy, one way of thinking about it. And as the cloud starts to warm up, it starts to dispel whatever gas and dust is starting to collapse around the star. Remember, we're starting with a cloud of hydrogen and other bits and pieces. There's going to be other heavier elements in there, and there's going to be specks of dust as well. So it's not purely hydrogen, it's hydrogen, mainly hydrogen, but other stuff as well. As the star starts to warm up, it starts to expel simply by radiating out all of this gas. And after about 10 million years or so, we're left with a star at the center and nuclear fusion starts. In other words, the star is at this point hot enough that hydrogen can fuse into helium. What is a little bit surprising is it takes so long to happen. So in other words, it takes millions of years for the cloud to collapse, all the while getting hotter and hotter and hotter. And it's only after about 10, 20, 30 million years or so that nuclear fusion actually switches on, and then we have the ignition of our star, our sun. After that, the cluster in which our star was born starts to drift apart. So in other words, we start with a large cloud of hydrogen. This is a Hertzsprung-Russell diagram reminding us where we are in terms of plotting all stars as a function of luminosity on the vertical scale and temperature on the horizontal scale here, coming back to the earlier question about all stars being different temperature. There's our sun. It is surface temperature of about 6,000 Kelvin or so. Some stars are much hotter, some stars are much colder, some stars are much brighter, some stars are much dimmer. We think our sun was born into a family. It probably had thousands of siblings. Stars are generally born in clusters. Generally, you do not get a cloud of hydrogen collapsing into one star. There will be enough material in a cloud of hydrogen to make hundreds, if not thousands, if not tens of thousands of stars. So we think our sun was born into a cluster, but over time, the cluster has drifted apart and we're now left with a star on its own. It is almost impossible to tell, because it happened so long ago, which particular cluster that might be out there was the original birthplace of our sun. They've simply drifted apart and we can't wind the clock back to tell which cluster produced our star. We know that if we look, for instance, with the Hubble Space Telescope and look in detail at what's going on for some of these stars right in the middle there, this is a star system seen edge on, looks more like a hamburger the way you look at it here. The dust of what's going on as the star collapses, as the hydrogen cloud collapses and all the dust is swirling around the star, it's almost impossible to see the star itself. So what you're actually seeing is the star lighting up the dust either side of a obscuring band of dust that goes right down the middle. So the starlight is lighting up the disk. This is what a protoplanetary disk looks like. We saw something similar in the earlier presentation. This is a whole load of dust that's circling around this star. This is not taken with an optical telescope. This is taken with telescopes that are sensitive to the rather cool material circulating around the star rather than the hot star itself. And these so-called protoplanetary disks, these disks of gas and dust that ultimately will become the planets, these have been proven to be rather more common than we first thought. There have been lots of them found. So here's a little zoo of lots of these disks that have been found. So we are looking at stars where the planets are in the early stages of formation. These were not taken by optical telescopes. These were taken by radio telescopes. This particular array is sitting in the Atacama Desert, and these are particularly well suited for looking at really cool things like the dust around a star. Optical telescopes are great for looking at hot things like stars. If you want to look at really cool things, you tend to go into the infrared, or in this case, into the tail end of the radio spectrum. So let's get an idea of how we go from a whole disk, which is basically just dust. How do we get from there to planets? Well, we think everything just grew by accretion from objects the size of nanometers or microns all the way up to objects that are gigameters in size. And we think it's simply a question of all of these things aggregating together. The precise mechanics, we still have to work out some of the details. If we think of where Earth and Jupiter are in terms of their mass, they're indicated by the positions indicated by the arrows. I haven't attempted to get the actual icons the right size, just the arrows are placed roughly where Earth and Jupiter are. So we start with a whole load of tiny grains of dust, which are not very regular. By definition, they are just sticking together in a very irregular fashion. And then these dust grains eventually stick together simply because they are very sticky and there are atomic forces which are holding them together. At some point, we start to grow until those things end up the size of pebbles. And then we ask ourselves, well, how do those pebbles stick together? Because if you take a pebble and hit it with another pebble, they'll just bounce off each other. So what is it that makes pebbles stick together? We don't really understand some of the details of how we go from tiny dust grains up to things the size of asteroids. But somehow something is holding them together until we get to the point where gravity can take over. Once things are kilometers in size, then gravity will start to pull them together. So to start with, it's atomic forces. Ultimately, it's gravity. Not too sure what's happening right in the middle there. But in terms of the timescales, well, we've got dust starting to form right from the very early part of the hydrogen cloud collapsing into a star, and then we'll start to grow until we're kilometer sized or hundreds of kilometers size or thousands of kilometers size after many, many millions of years. That's roughly the time scale indicated by the sizes here. But based on that, you would say to yourself, well, if that's what happens, small things grow into big things, then surely Jupiter was the last planet to be made because it's the most massive planet in our solar system. And that would be what you assume if it's a very simple process whereby small things get together and make bigger and bigger things. But it is thought that's not the case. From running simulations of how we think the solar system was put together, it's not the case that Jupiter was made last, despite the fact that it's the most massive. If anything, it is very likely that Jupiter was made first. So how can you make a big planet before you make small planets? That doesn't seem to make sense. And it's only by running simulations in computers with billions of objects floating around to try and get an idea of how gravity is working in these early stages of protoplanetary formation that we've gained an understanding of what we think is actually going on. One crucial concept is the frost line, or the ice line, or the snow line, depending on who writes the paper that's talking about it. Basically, there's a point in space which is defined by any particular star. Again, some stars are dimmer, some stars are brighter. But for any given star, there's a point at which various molecules like water or methane or ammonia, there's a point at which they freeze out. And beyond that point, these compounds are ices. Any closer than that, the star is producing so much radiation, these ices effectively melt and vaporize, and so you have a whole load of gases up to the frost line, and you have a whole load of ice beyond the frost line, which is why it's called the frost line. So the position in our solar system is about 5 astronomical units. It's between Mars and Jupiter. It's roughly where the asteroids are. For different stars, it'll be in a different position, but the same concept applies. And the fact that ices exist in some part of the solar system, but only gas exists in the other part of the solar system, that means that the evolution of planets beyond the frost line is completely different from the evolution of planets this side of the frost line. So let's have just a very quick think about how that might look. Here is the size of a planet on a vertical scale as a function of time. Million years, 3 million, 10 million, etc. We can't be absolutely sure, but we think the rocky planets grew something like that. The rocky planets grew this side of the frost line, inside the frost line, so they accreted all of the gas that was floating around and some of the heavy elements. That's why we find the Earth's crust is full of heavy elements. But Jupiter formed on the other side of the frost line. It formed in a region where there was loads of ice, and therefore it could mop up and hoover up huge amounts of ice beyond the frost line, which meant planets like Jupiter and Saturn and the ice giants grew in a similar way to the Rockies, but then they really took off. Once they had enough gravity to pull all of these ices in, they basically just avalanched or snowballed, almost literally snowballed, in pulling together all of the ices that existed beyond the frost line. So Jupiter took off really fast and the rocky planets came later. So although it's a little bit counterintuitive, we think that this is what actually happened. Jupiter, Saturn and the ice giants actually started to form first because they were in the right place beyond the frost line to do that. And the rocky planets only started to form after all of the various gas and dust had been cleared away from the inner part of the solar system. And then the rocky planets, Mercury, Venus, Earth, Mars, started to form beyond that point. I keep forgetting to mention that Thea is only written there just as a sort of reminder that that is the time at which we think a hypothetical object called Thea, which is about the size of Mars or so, crashed into Earth and produced a huge amount of material spalled away, and that ultimately became our moon. So we think we have a ridiculously large moon compared to anybody else in the solar system, or indeed anything else we found beyond the solar system. We have a large moon because an object hit us about 4.5 billion years ago, and effectively some of the material that was stripped away from the Earth ultimately coalesced into what we now call the moon. So what matters for this is, well, we still have questions. Simply to say Jupiter formed first is shirking the issue. We have lots of things to answer, like Okay, Jupiter formed first. If Earth formed inside the frost line, why do we have so much water? Water can't have been there, it can only have been gas inside the frost line, and yet we seem to live on a planet which has, well, not huge amounts, but a fair amount of water. It's sloshing around on the surface. Where did all of Earth's water come from? There's a thing called the late heavy bombardment, because we believe the early Earth and the early Moon were bombarded by a lot of material about 4 billion years ago. Why was there a huge amount of bombardment of the inner solar system 4 billion years ago? Why is Mars so small? It is a lot smaller than Earth. Earth and Venus are very similar in size, so why isn't Mars sort of the same? Why is it only 10% of the size of the Earth? That is a big difference. It's not just slightly smaller, it is a lot smaller. And can we explain why it is that outside Neptune there's a large belt, a so-called Kuiper belt of icy objects, and we believe that the entire solar system is surrounded by the Oort cloud, which appears to be a reservoir from which comets come. We see comets all the time, and they appear to be coming from some remote place, which we've hypothesized is the Oort cloud. So can we explain the existence of these things? Why do we think there's been a lot of bombardment in the early solar system? Well, one way is by looking at the Moon. It's difficult to tell on Earth because Earth has an atmosphere and weathering gets rid of evidence from a long time ago. But if we look at Mercury or look at the Moon, we see a lot of craters, and we can literally count how many craters there appear to be on the Moon. And we have reason to believe that the various mare, the seas on the Moon, are flooded basalt. And we can date that from Apollo and other places. And we think that about 4 billion years ago, these seas flooded with basalt. And notice that they are very smooth. There's very few craters in these regions. If the bombardment of the Moon that produced these craters continued after 4 billion years ago, why aren't there lots and lots of craters there like there are elsewhere on the surface of the Moon? So it looks like there was a heavy bombardment 4 billion years ago, which for some reason seemed to tail off. And we call that the late heavy bombardment. It took place about 4 billion years ago. So any hypothesis about the formation of the solar system not only needs to explain where did the water come from on Earth, we have to explain why there was a bombardment 4 billion years ago, which then appeared to not necessarily stop, but definitely slow down. So then we come back to speculation. We think this is the order in which things happened in the solar system. The big planets were made first, and then the rocky planets came second. But in terms of explaining water and explaining the heavy bombardment, there were two things that we think disrupted the early solar system. If these didn't happen, the solar system would look rather different than the solar system we see today. It is hypothesized, simply to try and explain the facts, that two things happened: a disruption to the inner solar system and a disruption to the outer solar system. And we're going to call those the Grand Tack and the Nice model. Not the Nice model, the Nice model, because it's based on work done at the University of Nice in France. First, let's look at the Grand Tack. This is a hypothesis which fits the facts. That doesn't mean it's right, but it's a hypothesis which, if true, would explain certain things about the solar system. The Grand Tack, if you think about tacking in a sailboat, a tack is when you move one way and then move another way. So we think that Jupiter and Saturn have tacked. In other words, the orbits of Jupiter, Saturn, Uranus and Neptune used to look like this. We're ignoring the rocky planets because they haven't formed yet. This is early enough before the rocky planets. So there's Jupiter, Saturn, Uranus and Neptune. And there are a whole load of small rocks around still yet to make up any other planets or asteroids or anything in the solar system. Some of them are close to the sun and they effectively have no water, and they're color-coded red in this diagram. And there's a whole load of little rocks or planetesimals further out, and they're color-coded blue. And we're now going to run the animation. What happens is the orbit of Jupiter shrinks and starts to bulldoze its way through all of these planetesimals and start to redistribute them. And then Jupiter and Saturn come back out again and start expanding their orbits. Why do the orbits of the planets change? That's a very complicated problem, and that's why we need simulations to try and understand this. We think it's the gravitational interaction, simply to say a planet is going around the sun and a planet is pulling on all of these rocks and all of the gas in the system. Well, that's true. But the reverse is true as well. Every atom of gas, every tiny little rock is also pulling on the planets. So it's a very complicated interplay between the gravity of the planets and the gravity of everything else. And this is one solution that says if this happened, that explains why we have all of this scattered material everywhere. Let's run that again. Jupiter orbit shrinks and scatters a lot of material, and then Saturn joins it. There's Saturn, and then Jupiter and Saturn both start to expand again. Again, it's very complicated to work out why should they shrink and why should they expand. It depends on the planets themselves, and it depends intimately on how much gas, how many rocks are inside the orbits and outside the orbits. And it's very sensitive to how the simulations run, which is why some people aren't necessarily convinced that this is necessarily the explanation. But if we think about what's going on mid-tack, look at where Jupiter and Saturn are. Jupiter and Saturn are now much closer to the sun than they were, and they've started to scatter all the material that used to be there. That's now scattered, and look at how much red there is now in the entire thing. The red was concentrated in this region, but now the red has been scattered, and a lot of the asteroids have picked up the material that used to be in the inner part of the solar system. So once the tack, as it were, is over, Jupiter and Saturn are now closer to where they are now, much further out in the solar system. And notice that the orbit of where Mars eventually would like to form, that's been depleted because Jupiter has bulldozed its way through the inner solar system and scattered a lot of the material that used to be there, waiting for Mars to form. It's no longer there. So Mars has now got very little material to hoover up to make the planet. Earth and Venus are still okay. They can make the planets that we know and love, but Mars has been disrupted by the proximity of Jupiter. Let me just take it one step at a time. I know it's complicated. So the Jupiter got smaller and smaller and scattered all of the red material inside and scattered it all over the solar system. Sometime later, after a few 100,000 years, Saturn starts to migrate inwards as well. Saturn is a much lighter planet, and for reasons I'm not going to go into, it migrates a lot faster. When eventually Saturn catches up with Jupiter, it starts to affect the way Jupiter is migrating, and it actually starts to pull both of them back out again. So at that point, they start migrating back out to the outer solar system and then settle down in their orbits out there. The Grand Tack took about 500,000 years. This is relatively early on, remember, before the rocky planets, and it explains why Mars is smaller than the Earth and Venus. So that's the Grand Tack that took place at that particular point, basically a fraction of a million years. It only took 500,000 years to happen, and it started perhaps a few million years after the solar system formed. It explains some of what's going on and why we have an asteroid belt, because of the scattering of all of the rocks that Jupiter produced as it bulldozed its way into the inner solar system. But to explain everything that's going on, we also need to think about what's going on in the outer part of the solar system. And that's where the Nice model comes in. It's a similar sort of thing in the sense that it's a change of orbits, but a completely different mechanism. And it's happening in the outer solar system, and it's happening at a very different time. If you look here, it's happening hundreds of millions of years after the solar system formed, not before the rocky planets. The rocky planets now exist, and this is changing what's going on in the outer part of the solar system. So we're changing scale here. We're now looking at Jupiter, Saturn, Uranus, and Neptune, and what's happening outside those orbits. If we run a simulation, again, it's very difficult to see what's going on. Some of it you'll have to just take my word. The disk out here is a large, dense disk of rock and ice, planetesimals, that was left over when the cloud collapsed and the star formed. But it's nowhere near enough to explain, for instance, this enormous Kuiper belt of objects which goes beyond Neptune and goes an enormous distance, and also the Oort cloud beyond that. Because although it shows it as a rather artificial sharp edge, most of the material we think in the very early solar system was confined to a few hundred or so AU, astronomical units, the distance between the Earth and the Sun. So what is it that the NEAS model predicts? Well, if you run what's happening with these, as again the planets interact with all of this icy material outside these orbits, something dramatic happens when the period of Jupiter happens to coincide with a multiple of the period of Saturn, or actually the other way around. In other words, there's a resonance. If they are all orbiting the Sun in completely random orbits, nothing much happens. But if you find a situation where Jupiter orbits twice in the same length of time Saturn orbits once, or if you find that Jupiter orbits twice in the same time that Saturn, wrong way around, Jupiter orbits 5 times in the same time that Saturn orbits twice, whenever you get a multiple or a submultiple, you can get a resonance because the planets start tugging on each other, and if that tug adds up year after year after year after year, because they are locked into a particular periodic step with each other, then you can get these planets pulling on each other and changing the orbits. And this is what they think actually happened. If we run the simulation, again, let's run it from t equals 0 for quite a few million years. Nothing much happens. A little bit of jiggling perhaps, but nothing much happening. But at some point, bam, they get into resonance and suddenly they pull each other out of orbits, and there's a sudden rearrangement of the outer solar system. What's happened to all the material in the outer solar system? It's all been scattered. Some of it is scattered into the inner solar system, and that is why we get all of these icy objects raining down on the early Earth, filling our oceans. That's where the water comes from. It comes from the outer part of the solar system because these outer planets have changed their orbits, disrupted all of these icy particles, some of which have been thrown out to form the Kuiper belt and the Oort cloud, some of which have been thrown in and provide the inner solar system with its water. That's why we have oceans. And you probably didn't notice, but actually Uranus and Neptune actually swap over. If I look at the original one, Jupiter, Saturn, not Uranus, Neptune. Neptune is inside Uranus, but when you run the simulation, although Neptune starts inside Neptune, once the simulation hits the resonance and you suddenly get a change in the orbits, they swap over. So it is quite possible, again, we can't prove this, but it's quite possible that Uranus and Neptune are not only not at the same distance they are now, they might even have been in a different order in the very early universe. But the planetesimals that used to be in the disk have now been scattered into the inner solar system. That's why we had the late heavy bombardment. This occurred 4 billion years ago, and that's why the moon is so pockmarked with apparently 4 billion year old craters, because this produced an awful lot of cratering of the moon and Mercury, and also those icy bodies provided us with the water. So it's a very complicated evolution. It is by no means simple to say if you make a star, you make planets, and the planets simply sit there and coalesce out of the disk that is resulting from make a star in the middle, whatever's left simply coalesces into planets. It might be that simple. It certainly wasn't for our solar system. And one reason to study exoplanets is to get an idea of, is this common? Does this often happen, that we get a rearrangement of the solar system over the early evolution of the solar system, which results in an arrangement of planets which is quite different from what they looked like in the very early part? And that's one of the reasons we think why we find with exoplanets so many Jupiters close to their stars. Our Jupiter is quite a long way away, beyond the frost line. How can you have a Jupiter that close to a star? We found quite a lot of them. Surely you can't make a Jupiter close to a star because it's made of ices. But no, we think that other exoplanet systems have suffered the same fate. Their Jupiter was probably made a long way from their star. Jupiter has migrated inwards. Maybe their solar system didn't have a Saturn to pull it back out again. So the Jupiter is left fairly close to their host star. The more of these exoplanets we study, the more we can figure out whether this is a reasonable explanation or not. But the take-home message is the solar system is not a clockwork orrery. It is not simply made that way and it will work that way for the next 10 billion years. The solar system was chaotic, and arguably the solar system is still chaotic. We can't calculate where the planets are going to be a long way into the future. Everything looks nice and serene at the moment in the sense of how the planets are going around the sun. But we can't tell whether Jupiter will go back to its old ways and start to bulldoze other objects out of the solar system at some point in the future. Probably not the near future, but who knows? Thank you.